Okay. Hello. Good afternoon, everyone. Thank you, sir, for giving time and facilities for our presentation in this session. Please permission to all attendees. My name is Nurman Firdaus. I am affiliated with the Research Center for Hydrodynamic Technology, National Research and Innovation Agency of Indonesia. I, as the first author, represent all author present paper entitled The Effect of Floater Geometry on the Dynamic Parameters of Spar-type Floating Offshore Wind Turbine in this symposium. In our presentation at this symposium, IRIS 2023, there are 5 outline consists. First, introduction. Second, method. Third, validation. Fourth, research and discussion. And finally, and conclusion. We know that most of the fossil-based energy reservoirs and several production countries have experienced a decline in exploration. So therefore, currently the most countries are looking for and studying the demand for clean energy in the form of solar-based, wind-based, tidal-based, and so on, is rising in the recent decade as high intensity of environment degradation to harvest material for fossil-based fuel. According to the International Energy Agency, the electricity generation of wind power increased about of 273 terawatt-hours, or up 17% in 2021. Floating wind turbines are one of the most efficient renewable energy alternative that utilize potential location in the sea area. In the recent years, the offshore wind farm is rapidly expanding toward the deep sea to cope with accelerating demand for zero emission. The figure on the left shows the platform structure of fixed bottom and the floating wind turbine. The stable floating to support the operation floating offshore wind turbine was considered in the design system. The harvesting of offshore wind energy can be supported using various types of floating platform, as each type has characteristics in field application. This figure describes the form of floating platform that can be used for supporting structure on wind turbine pools. They are bar-shaped, semi-sharp, spar, and tension leg platform or TLP. Based on various in deep sea area, the main contribution dynamic response to floating offshore wind turbine platform system is generally caused by the hydrodynamic and hydrodynamic load. Based on the various type, the floating platform, spar-type for the FOVT platform have the simple shapes and are one of the easiest and cheapest to product. From here, as the only effect on the hydrodynamic parameter is the geometry of the spar-type are changed. This slide describes the method used to calculate the dynamic response, the geometric influence of the spar. The numerical computation technique used to calculate hydrodynamic parameter for geometric effect on the spar is the boundary element method. The boundary element method solves the potential velocity of scattering and radiating for the floating body to incident waves. In this present conference, we obtain hydrodynamic coefficient based on the frequency domain using an open source BEM solver NEMO from Nantes to France. In order to the fluid model in motion, the BEM solver assume that the fluid flow is incompressible, infinite, and irrotational to a set of equations for the linear potential flow theory. This figure shows the component of the boundary condition in numerical calculation. In the study, the validation procedure in the boundary element method modeling to ensure the numerical result with applicable theory was carried out and compared with the other BEM solver. We adopted the floater of OCT high-wind spar floating offshore wind turbine with the boundary element method model published by MA et al. 2021. Here are some figures and you can see them. The figure A and the left show the main dimension of the spar OC3 high-wind floater design. The figure B on the middle show the mass NEMO result of spar OC high-wind. And the figure on the middle show OC3 high-wind model design from previously published author. This table describes other parameters which are mass, center of gravity, and draft. This will show the result of validation that has been done. You can see the validation result in this figure. The figure on the left, E, C, and E, show the hydrodynamic coefficient of added mass, while the figure on the left, B, D, and F show the hydrodynamic coefficient of damping for source, heave, and pitch. The mass considered for the hydrodynamic model to represent the body surface in the present model have a total of 1,900 of panel. The boundary element method solver setting obtain the result of well correctness. You can see the compare the result present and BEM model. The model calculation is used to compare the performance of various floater geometry for the next spar floating offshore wind turbine. The slide presents geometrical variation of the spar compared in the study. The comparison of spar geometric size was carried out by referring to the volume OC3 high-wind type bed change in the base diameter length of floating platform. You can see and understand clearly in this figure. The spar one have the base diameter of main floater platform about of 11.39 meter, and the base length about of the 72 meter. So total draft of platform is 84 meter. The size of the spar you can see the data in the figure and table on the slide. This is discussion of hydrodynamic coefficient added mass. The magnitude of added mass or inertia for the short, heave, and pitch mode are shown in this figure. The hydrodynamic coefficient in the current work are denoted by a black line for spar 1, blue line for spar 2, red line for spar 3, and green line for spar 4. For the source and pitch mode, the spar which has a smaller pitch diameter, longer floater tends to have greater added mass than the other. Conversely, for the mode case of heave, the value of added mass is greater in the spar shape which has a larger pitch diameter and shorter floater length. The result damping also in this figure. The damping radiation in the short and heave on the spar with larger base diameter and shorter floater tends to have larger values than other dimensions. There are phenomena decreasing damping which are most similar for all spar. You can see curve in this figure. For the heave peak value of damping on all spar occur at around 0.88 rad per second. For the pitch, you can see figure C. The damping radius is greater on the spar with smaller pitch diameter and longer floater, and the peak value almost occur at around 1.146 rad per second for all spar. In this slide, the motion characteristic due to the influence of changing geometry size are shown. For the air outward shot, you can see figure A indicate that the response peak are caused by the frequency resonant pitch response. The motion response of spar 1 looks bigger than the other spar. In fact, the sub response peak greatly affected by the mooring restoring force and occur at low frequency. For the response peak pitch, you can see figure C. The peak response occur in spar 4 due to lower damping value. For the arrow heave in figure B, the spar 3 exhibited the biggest response among the other spar shape. All motion response on different spar shape have different frequency peak, which indicate the natural frequency of its spar shape X source mode. Based on the previous discussion, some conclusion of the floater performance floating of when turbine type due to geometric effect can be explained as follows. First, the hydrodynamic coefficient of the spar platform show a significant difference linearly due to change in geometry shape. Even top floaters have the same displacement volume below sea water level. The peak frequency of added mass and damping in the source, heave, and pitch motion tends to be close to the same in all variations of the spar shape. Second, in general, each spar shape has different motion characteristics, besides being influenced by the dynamic parameter of the hydrodynamic coefficient. The motion response is also strongly influenced by wave excitation restoring force. This parameter causes the nonlinear different response peaks in the case difference spar geometry. Okay, thank you very much for keen attention.